Hi everyone! In this video, we're going to focus on how to iterate over a data structure using a for loop. So we'll first learn the syntax, and then we'll practice writing a couple of functions that iterates over a list and accumulates data along the way. Finally, we'll try to generalize this pattern using a higher order function. Sound good? Okay, let's go. In Scala, we write a for loop by using the keyword for. And then between parentheses, we define a variable, in this case number, followed by an arrow pointing to the left. And finally, we mention the data structure we want to traverse. Here it's a list. So what does the for loop do? It iterates over the list by successively assigning the variable number to an element of the list. Then it executes the code block between the curly braces. Here, as you can see, we simply print a sentence. This syntax is similar to what you might find in other programming languages. There is just one significant difference: the S before the double quotes. This is called the S string interpolator, and it allows us to evaluate variables inside a string. This is why we see the numbers 1, 8, -3, and 12 in the printed lines. So if we remove the S before the double quotes, the code will print the phrase number is $number 4 times. There are a few other string interpolators. For example, in the standard library, the F string interpolator, which customizes how to print a floating point number. As we can see with pi here, we only display the first two numbers after the comma. And we can also define custom string interpolators, which is something mostly done by libraries to format an SQL query or a JSON document, for example. Cool, so let's go back to the for loop example and talk about braces. We can remove the curly braces from the code block inside the loop only if it contains one line of code, as it is the case on the left-hand side. But if we have a code block with several lines of code, as is the case on the right-hand side, then the curly braces are mandatory. Again, this is not specific to for loop. The same rule applies to function and method definitions. By the way, there is a new feature in Scala 3 that gets rid of braces entirely and rely on indentation instead, like Python. If you want to read more about this new syntax, you can find more information below this video. Okay, so now the question is the for loop hard-coded to list? Or can we use it on any data structure, such as array or vector? Or even on custom data structures that we have created ourselves? It turns out that the for loop is just an alternative syntax for the function for each, which we can see here. This means that we can either use for loop or for each. It doesn't matter, it's just a question of style. And at the bottom, we can see that the signature of for each for list. It's a parametric method that takes a function from A, the element type of the list, to 2, a parametric type that's completely unconstrained, meaning that we can choose whatever we want. And for each returns unit, which is equivalent to void in other programming languages. This means that the result type of this method is kind of useless. We only use for each for its effect, such as updating a variable or sending an email. So in a sense, for each is very similar to map, except that we don't get an updated list at the end. Therefore, if we create a new type, such as point, that includes the for each method with the appropriate signature, then we can use a for loop to iterate over an instance of point, as you can see here. So a for loop is quite convenient because it provides a unified syntax that we can use to iterate over all objects that contain or produce data. Before we move on to the exercises, I would like to show you one last feature of for loops, that we can iterate over several data structures at the same time. For example, here we have two lists, one that contains shapes and another that contains colors. we can put those two lists in the loop definition, and it will be equivalent to calling for each on the first list, the shapes, and then inside the action block, it will call for each on the second list, the colors. In other words, it will first select a value from the shapes, then it will iterate over all the colors, and once it's done, it will go to the second shape and repeat the process over and over until it has iterated over all the shapes. Does that make sense? Great. So this technique is quite convenient because it avoids us creating multiple levels of nesting and indentations. It's an efficient way to transform code that has multiple callbacks into a single for loop, which is much more readable, right? And this syntax is heavily used in real-world code bases, and we'll practice working with it quite a lot in the last two sections of the course, where we talk about actions and error handling. And since for each doesn't care about the result type of the action block, we can easily mix and match different data types within a for loop. For example, here we iterate over both a list and a point. Okay, so our main goal in this section is to process a large data set and extract some interesting facts about it. So let's go back to this use case, starting with a very simple example, so that we understand how it works, and then we can complexify it. Sound good? Okay. So let's say we have a list of numbers, and we want to calculate the sum of its elements. How can we do that with a for loop? Well, first we need to define a variable, let's call it total, that will store the current value for sum. So we set its value to 0, and then we use a for loop over the list of numbers, which give us access to every single integer inside it. Then within the loop, we increment the variable total by number. We can either do that explicitly with total equals total plus number, or we can use the shortcut total plus equal number, which is a widely used operator in imperative languages. And at the end of the method, we just return the variable total. Cool, so let's visualize how this works. We start with the variable total, which is equal to 0. Then we process the first item of the list, which increments total by 1. Then we process the second item of the list. Now total is equal to 9, then 6, and finally 18, the expected result. You might be surprised that I'm recommending using a for loop with a mutable state in a functional programming course, but it works and it's simple. And actually in the next chapter, we'll cover why immutability is often recommended in FP, but for now rest assured that code like sum is completely fine. So it's finally time to practice. Can you please open the file for loop exercises in your favorite IDE, where we're going to implement a couple of methods using for loops so that we can familiarize ourselves with this syntax. First, we'll try to implement size as a method that calculates the number of elements in a list. This method already exists in the standard library, but our goal here is to re-implement it using a for loop and a mutable state as we did for sum. So I'll let you pause the video and try to implement and test size yourself. Don't hesitate to search for interesting property-based tests in order to make this exercise more challenging. Cool, so we can write code that is very similar to sum. So we'll start by defining a variable, let's call it total as well, and assign it to 0 because this is the number we will return in case the list is empty. Then we know that we'll return it at the end, and in the middle we have our for loop. So we start the for loop, we define the variable item, left arrow, and then the list. And then within the loop body, what do we want to do? We want to bump total to 1. So we can do plus equal 1. That's it. Now a quick refactoring we could do is that you see this item, this variable is grayed out because we don't use it. So a good practice in this case is to use an underscore just to make it clear that this variable will never be used. And since the code is so small, I think it actually looks quite nice in a line like this. But formatting is really up to you, whatever you like. Okay, so now the question is, how do we test size? In for loop exercises, you will find that I already wrote a couple of unit tests. At the moment, they are ignored, for at least for size, min, and word count, because these methods were not implemented yet. So if you want to activate the unit test, replace ignore by test, and then you can run all the tests over there, or using SBT if your IDE doesn't support it. Cool, so now that we see that sum and size test pass. So these test examples are not bad, but they don't cover much of the domain. So let's try to find some useful properties for size. One thing we could do is to try to think about how size interact with other methods from the list API, in particular list concatenation. So imagine we say test for size and concat. So how do they interact together? So let's generate two lists. Let's call them list1. Could be a list of string. It doesn't really matter. It could be a list of string, a list of int. What we just want is two lists of the same type, and list2 of the same type. Cool. So once we have those two lists, if we calculate the size of each list, so we say like size 1 will be the size of list 1, and the same for size 2. What will be the size of the concatenation of list 1 and list 2? Well, it should be equal to the sum of the size of list 1 plus the sum of list 2. So this is what I mean, is that we should be able to say that list 1 concatenated with list 2. So this plus plus means list concatenation. So if we put those two lists together and we calculate the size of this, it should be equal to the size of the first list, size 1, plus the size of the second list, size 2, right? So if we have a big list and we break it down into pieces, the sum of the big list is equal to the sum of the size of every single piece. Let's try to run the test. It works. All good. If you have other ideas for size, don't hesitate to comment in this video or to talk about your answers in Slack. Cool, so let's move on to the second question. So let's go back to the exercise file. Next, we're going to implement min, a method that takes a list of numbers and try to find the smallest value in this list. So when the list is empty, there is no minimum value. That's why we return the return time of min is an option of int and not an int. Option is an enumeration with only two cases. It's either a sum when there is a value or none where there isn't. For example, if we call min on the list 2518, we'll get back sum of 1 because there is a minimum value which is 1. But if we call min on the empty list, we'll get back none because there is no value in the input list. Cool, so now it's your turn to implement min. Please try to do it using a for loop as we did before. Cool, so to implement min, we'll open some curly braces, define a variable, how do we call it? Let's say state, that will store the min value that we have seen so far. What do we initialize it to? Well, we need to initialize it to the value we should return in case the list is empty. So as you can see, it's none. Let's do this. Then we know that at the end we return state. And now in the middle we have our for loops. So this will say define a variable number, left arrow numbers. And now within the for loop, what do we do? Well, there are two cases. Either the state is empty, it's none. Then in this case, we want to set the current value, number. This will be only the case for the first item in the list. But then if we are later on, we will have a state that is non-empty. In this case, we want to compare the value within the state with the variable number. So how do we do this? Is called like a case analysis. It's a fancy word to just say state is an option, is an enumeration, and we want to do something different based on the two possible cases. So the solution for this is to use a pattern match. So we'll say state match. And for each of these options that state can be, we'll have two different lines. So we'll say case, it's a none, then we put an arrow. Case, sum, current min. So here current min will be the variable of the int that will be the current minimum we have seen so far. And actually IntelliJ tells me that it doesn't compile, and we can see the error. It says that it found a sum of A, but it required none.type. So this is a very annoying error that we have in this specific case in Scala. And it's related to the type of state. So here we want state to be an option of int, right? This is the type we return at the end. But if we ask IntelliJ to tell us what is the type of state, because we didn't annotate the type, so we let the Scala compiler to figure it out. So if we look at the IntelliJ tells us that it's either an option of nothing or none.type. And so what happens is that none is a bit peculiar. So none, if you look at the definition, it's an object and it extends option of nothing. Nothing is a very weird type. It basically means in this case that it's kind of a wildcard. It will be an option of int, an option of string. It will adapt to anything we want. We'll talk about nothing later on. But so what happened in Scala is when we don't provide any information to the compiler and it needs to infer a type, like as he had to do it here, we didn't give it any hint of the type we expect for state. So in that case, the compiler infers the most precise type for the expression we pass. And the most precise type of none is none, actually. It's not an option of int, it's none. So it's annoying. So what we need to do here is to be explicit and say option of int. And in this case, you see everything compiles now. Another way to do this is instead of annotating the type, you can use, instead of using none here, you could use option.empty and specify what type do you expect. Generally, we don't need to do this, but in a couple of cases we do. This is because the type inference in Scala is eager, meaning that it needs to make a decision right now. It can't wait for later on, for later information to figure it out. Okay, so this is just a corner case. Most of the time we don't need to do this. Okay, so now the question is, what do we do if the state is none? So if the state is none, it means that there is no minimum value so far. So we can replace the state and set it to a sum of number. Yeah? And if there is a current minimum value, here we need like kind of an if then else. We say if number is strictly lower than current min, then we do set the variable only in that case. It will be sum of number. This code will work, but I'm always a bit careful about this. You know, did I use the right comparison? You know, should I put current min first or number first? There is always a source of confusion. Another way we could have done this is use the function min between numbers. So we could have said number min current number, current min. In this case, min, this function here, is not the same as this one. It's the min between two numbers. And this function is going to return the smallest number among these two. So I find this way, at least we are sure that we are not going to screw up. Okay, so let's go back to the test file. Let's remove the ignore and use test instead. And let's run the unit test. Cool, it works. Now, what sort of property-based test could we write for min? Do you have any idea? One thing we could test is that actually the value returned by min is actually the smallest value in the list, in the input list. So what we could do is to say test min returns a value smaller than all elements in the input list. Yep. So here we'll generate one input variable, one input list. So let's call it numbers, and it's a list of ints. Then what do we want to do? We want to call min on this input list. So we'll say min of numbers. This is going to return an option of int. So again, we can do a pattern matching in this. And actually, I haven't shown you that, but IntelliJ offers something called like exhaustive pattern match, which is what I recommend to do. So if we click exhaustive pattern match, IntelliJ will write for us this case sum, case none, which is very convenient. So we can say that here, in case we do have a minimum value, then we can iterate over numbers. So we can say for each value in numbers, so for all numbers inside it, we expect it to be, we expect value to be smaller or equal to number. That's the definition of a value that is the minimum. And if it's none, it means that there is no input. So in this case, there is nothing really that we can prove. So we can just say succeed as like the test will pass if that's the case. Another way, so let's run the test. Let's see if it works. Yes, it does. Another way we could have done this is via a for loop. We could have said, okay, value, let's call it min value, maybe it's more readable. So min value will be the value returned by min in case it's a sum. And because this arrow is equivalent to for each, because we're in a for loop, then we can do number. So again, because here we were doing a for each, so we could have done it in a for comprehension. And then we move the assertion to the body of the loop here. Except now it's not called value, but min value. Let's run the test. All good. So this is an example of how to mix and match different types within a for loop. Here it returns an option, here it returns a list, and we do for each over both types. Cool. So this is a good unit test, a good property-based test. But you know, if min were going to return like a constant, like the smallest possible integer, then this property will still pass because, of course, the smallest possible integer is always smaller than any number in the list because it's the smallest number. Another thing we probably want to test is that the return value from min is actually a number that belongs to the input list, right? So let's try to write such a test. We could say test min returns a value that belongs to the input list. And then our test is going to be quite similar. We will generate a random list of numbers. Let's this time, so we call min on this input list. And let's this time use a for each, just to change a little bit. So this will be min value. Yep. And what do we want to verify is that numbers contains min value. So contain is going to iterate over the list, and it will only return true if the list actually has this number. So let's run the test. Cool, it also works. Nice. Now let's go back to the exercise file. And this time we're going to work on word count, which is a very well-known example for big data applications. Essentially, word count takes a list of string and calculate how many times each word is mentioned, so like their frequency. For instance, if we run word count on the list hi, hello, hi, we'll get back a map where hi is associated with 2 and hello is associated with 1 because the input list contains hi twice and hello only once. Make sense? Awesome. So please pause the video and try to implement and test word count using a for loop and a mutating variable. Cool. So let's start with word count. Now we start to know the drill. So let's define a variable. Let's call it frequencies, because this is going to store the map of a string to int. So let's say map.empty. And at the end, we're going to return it. So here we're in a similar case. We need, you see, we can see that it returns a map nothing, nothing. It's all, again, because the problem here is when we use empty, we didn't specify the type parameter. We let the type inference do its job. But because we didn't provide any hint about the type that we expect, by default, the Scala compiler infers nothing, which is not really useful in our case. So we have to be precise. Either we annotate frequencies to say that it's a map string int, or we put a type annotation here to say that the key must be a string and that the value must be an int. Again, this is one of the weird use cases where we have to be explicit. Most of the time we don't. Then we write our for loop where we say, okay, word, left arrow, words. And then what do we do within the loop? Well, we need to check what is the current frequency for this particular word. So we need to do a lookup within the map, and based on the response that we get, do something with it. So we'll do frequencies.get. So this will allow us to look up a value inside the map. So we say word. And get returns an option of v, an option of the value. So in our case, it will be an option of int. It's an option because maybe this key doesn't exist in the map. So now we can do, again, because it's an option, we can do an exhaustive pattern matching. And now it's much simpler. We just have to figure out what to do based on these two cases. In the case where we do have some existing frequency for that particular word, what do we do? Well, we want to update this particular frequency and bump into do +1. So we do frequencies. We want to update the variable, and we'll update it using the function updated, where we need to provide a new key and a new value. So the new key will be the same. It's going to be word, and the new value is going to be frequency +1, because we have seen this word one more time. In case it's a none, it means that we have never seen this word before. So in this case, we just set it to 1. Yeah? Make sense? So I actually quite like this code because it's very simple to read and understand. If we want, we can be a bit more fancy and refactor it a little bit. One thing that we realize is that here, what we do, we always update it, and in case there is no frequency, it's equivalent to 0 if you want. So what we could do instead is when we do this, we could calculate the current frequency. So we'll say val frequency, and we could say that it's equal to frequencies.get. And in case it's a none, we can use a method called get or else to say, in case it's nothing, we just set it to 0. We don't set it, but we just, instead of getting a none, we get 0. So then once we have this, we can have a single line of code next that says that we take the frequency and we do +1. If there was nothing, then it will be 0, then it means we'll set it to 1. If we had something, then we'll bump it by 1. And actually, IntelliJ tells us that we can do even more refactoring and use the function get or else. So it's really up to you. What do you find the most readable? I actually prefer, I think, the previous solution. So let's run the test. First, let's remove ignore, and we can run the full test suite. It passed. Awesome. What sort of property-based test do you think we could write for word count? Do you have any ideas? So one thing we can verify is that if we look at the type of word count, it returns a map string to int. But in fact, this int is not really precise because it's a frequency, so it must be strictly positive. It can't be 0 or it cannot be a negative value. So we could write a property test that verifies that this value is always strictly positive. So let's do this. Let's say test word count returns frequencies strictly greater, or let's put it in a symbol, greater than 0, strictly greater than 0. Cool. So let's generate a random list of string. So let's call it words. Yep. And what do we do with it? We're going to call word count on this list. Then this will give us a map. Then we can extract the values out of this. So values, this will give us an iterable, which is basically a lazy list of int. And we can use for each on this. So we can say, okay, so this will be a frequency inside of the list. And we want to assert that this number, this frequency, is strictly greater than 0. All good? Just to show you that it works, sometimes I actually never show the test failing. If we add use inferior to 0, it will fail, and it will say that 1 was not less than 0, which means the frequency 1 was bigger than 0. Cool, makes sense? Another thing we could test, because this test is not amazing, another thing we could check is that every single keys that are part of the resulting map must belong to the input list. Or in fact, the other way around. We could verify that for every single word of the input list, there must be a key in the output map that matches it. So I'll let you write this kind of property as an exercise. Okay, so let's come back to the exercise file. One thing you might have noticed is that sum, size, mean, and word count are quite similar. They all iterate over a list and update a variable along the way. So it will be great if we could capture this pattern using a single higher order function, and then we would refactor sum, size, mean, and word count to use this new generic method. Why is that good? Well, it will make the code simpler and more consistent. But most importantly, we know that at some point we'll want to process our dataset in parallel, and that supposedly doing so is not going to be straightforward. But if we find a way to parallelize the generic function behind data processing, then we will get a parallel implementation of sum, size, mean, and word count essentially for free, which will save us lots of time and effort. Okay, so please pause the video and try to implement a function that generalizes all the methods we have implemented in this file. You may find this quite difficult, as I haven't given you the signature or even the name of such a method yet. But it's a good exercise, because in practice, we are rarely given these sort of details. So good luck! Okay, so it's probably not obvious how we can generalize these four functions. One thing that might help us is to visualize their behavior. So here I'm displaying the input list for the functions sum, mean, and word count. And we can see that they all take a list as an input, and that the type of the list may vary. So pattern, the generic function that we are trying to implement, will need to take a list of A with values A1, A2, and A3, where A is a type parameter. Then each of these functions define a variable that is like an internal state initialized to 0 for sum, none for mean, and map empty for word count. So it seems that these variables all start with some kind of default or empty value that is very different for each function. In this case, let's assume we have a constant called default value that will be passed as parameter of pattern. Also note that default value may not necessarily have the same type as the element of the input list. For example, min takes a list of int, but the internal state is an option of int, not an int. Then for the next step, we process the first element of each list and update the state. So for sum, we do +1. For word count, we insert the key value hi1, and for min, we set it to sum of 1. So the pattern is not obvious. So let's process the second element of each list and see if we have more ideas. For sum, the state becomes 9 because we summed up the previous state 1 with the current element 8. And for word count, the state becomes map hi1 hello 1 because we took the previous state map hi1 and we inserted the key value hello 1. So now we start to see a pattern. In both cases, we took the current value of the internal state and we combine it with the element of the list that we are processing. So let's assume we have a combine function as an input of pattern, and we call it with the current state and A2. Finally, we'll repeat this process for the last element of each list. So state become combine state A3. Does that make sense? Okay, so let's go back to the exercise file and summarize what we learned. The generic function pattern must take a list as an input. So let's call it items. And it's a list of A. So let's define a type variable A. Then it needs a second input that will be this default value that we need to initialize the state with. So default value can have a type different than the input list, than the element inside of the input list. So we need to define a new type B and say that default value is a value of type B. Then we need a combine function. So combine is a function that takes two values. The first one is the current state, so it means it's a B. Then it takes a value from the list, so it's an A, and it returns a new state, so it's a B. And this function is going to return the final state at the end, so it's going to return a B. Cool. Let's do a quick refactoring. First, let's rename A to be from. So every single A will become from. And let's say B will become 2. So let's say 2, 2, 2. So this will make it slightly more readable. Another thing we might remember from the previous lectures is that when you have a fully generic functions like pattern, and we want to, and we have a val function as an input, then it's better to make this val function in a separate parameter list to use currying in order to get better type inference. Cool, so if you haven't implemented pattern yet, could you please pause the video and try to do so now that we know its signature? Okay, so let's implement it. So we'll need to define a state. So let's call it a variable state, and we initialize it to the default value passed in parameter. Then we know that we'll return this state at the end. And in the middle, we'll do a for loop over the list of item or elements. And what do we do within this for loop? We need to update the state. So we'll say state equal, and we'll update it using the combine function passed as parameter. So we'll say combine. Combine takes two elements, one of type 2 and one of type from. So 2 must be the current state. And from is a type of element inside of the list, so it will be item. That's it. Let's refactor it a little bit. Cool, and verify that it compiles. Yep, it does. Cool, so now how should we call this function? It turned out that it's a well-known function in FP, and it's even implemented on the list interface. It's called fold left. So let's rename it. I lost my shortcut, so let's do this, fold left. Cool. So now that we have fold left, could you please refactor mean, word count, size, and sum, and using fold left? So please pause the video and try it out. Cool, so for sum, let's use fold left now. So we'll need to pass the input list as a first parameter. Then we need to pass a default value. This default value is basically the value we used here to initialize our state, so it's going to be 0. Then we need to define a combined function that takes the state and a number. Both of them are int, so the state is an int, the number is an int. So the implementation is going to be state plus number. Cool. Let's run the test to verify we haven't broken anything. Yes, all good. What we can do also is that if you realize that we use state and number only once and we use them in the same order, so we could use the underscore syntax instead. So we could do underscore plus underscore, which will make this function extremely concise and really clear. What is how do you sum numbers? Well, you just fold it and you start with 0 and you just do plus over every single number. What about size? Size is going to be very similar. We take our list of items. The default value is also 0 because that's what we return if the list is empty. The state this time is going to be the combined function is going to be slightly different. So we take state and item. And what we want to do, so state is the counter that counts how many value have been processed, the current size of the list. So we just do state plus 1. As we know, we don't care about the item. Doesn't matter what is the value of the item. The size doesn't care about this. So we can use an underscore to make that clear. What about min? Okay, let's do this. So fold left of numbers. Then we'll use this for the default value. Here, for the same reason, we do need to use option of empty of int, or if we want to use none, we need to annotate it to say that it's an option of int. If we don't do that, then the combined function will not work. This is a very annoying issue in Scala 2, and people are working very hard, such as Scala 3 will not have the same issue. It's still a bit open for right now. But basically the problem is, if you just put none here, because we know that the type inference is done one set of parentheses at a time, when the compiler sees none, it infers the most precise type, none, which means that then in the combined function, we can't change it. We have to let the value as a none forever. So it's very annoying. But we have to deal with it for now, and hopefully it will be fixed soon. Okay, so now our combined function is going to take a state and a number, which means that now we can basically copy this bit of code here that was inside of the for loop. And instead of doing state and set it, we just return, we don't change any variables anymore. This is all handled inside of fold left. Another thing we could do here is that instead of defining a variable and pattern matching on state, we could pattern match directly on the inputs. But if we do that, we do need to change these parentheses to curly brackets. So it's a bit annoying, but it's when you want to pattern match on an input using a case statement straight away, you do need curly braces. So here, this time, we can say case none number, and we can say case sum current min number, and then move the code like this. So it will be sum of number and here sum of number min. Yep. So if you see what we do here, this is a function that takes an option and an int, and we pattern match on the option to say, okay, if the option is a none, we do something. If the option is a sum, we do something. And for number, we don't do anything. We keep it as a variable. So I find this implementation a bit more readable. And let's run the test to verify we are all good. Yes, we are. Okay, last function, word count. How will we refactor it? Again, I think by now you know the drill. Fold left words, we initialize it to map empty. Again, it's important to define the types, otherwise the combined function will not work. And then here we define frequencies, the state, and word. And then we can simply copy-paste the code here, right? Oh, as you can see, it's red because we are defining a val function here. This combined function is a val function. It's an anonymous lambda. But the body of the function is over 2 lines of code because first we define a variable, then we do something. And the problem with this is that, as I said at the beginning of the lecture, is if you need several lines of code, you need to use curly braces and not parentheses. So now it should work. Cool, all good. Great. So not only did we remove code duplication, but we also made the implementation of sum and size more elegant. However, min and word count are not necessarily more readable this way, which is a sign that maybe there are even more generic functions than fold left out there. So I'll let you think about it in your own time, and we'll come back to it when we try to parallelize fold left in the last video in this chapter. And before I forget, how should we test fold left? Fold left is a fully parametric function. As we can see here, it has 2 type parameters. So we know that it must treat its inputs in the same way, meaning that if fold left behaves as expected for one combined function, then it must also behave similarly for all the others. And since sum, size, min, and word count are now implemented in terms of fold left, and since we have written many tests for those methods, then it means that fold left is already well tested, right? That's true, but you might remember in the previous section, when we tested pair, that we had to choose the input very carefully to avoid special cases, such as when the fields first and second were equal. And it turns out that sum, size, min, and word count all have the same special behavior. Do you have any idea what it could be? It's certainly not obvious, but if you think about it, for all these methods, the order of the elements in the input list is irrelevant. We could shuffle or simply reverse the input list, and we will get exactly the same result. For example, for min, we don't care where the minimum value is. It could be the first element, the last element, or somewhere in the middle. In any case, the function min will always find it, right? So let me prove it. If we slightly change fold left so that we reverse the input list before we iterate over it, if our tests were covering everything, then the test should fail, right? But they all pass. This is because all the functions we have implemented don't care about the ordering. So if we want to improve the test coverage of fold left, which is already really good, we need to find a test example that checks that fold left processes the input list in the expected order, meaning from left to right. What could we choose? I'll let you pause the video and try to write this test. So what we could do is to write a test that verifies that is going to be a no operation. So something that takes an input list, do fold left with this input list, and return the same list at the end. So how will we do this? So let's call it a fold left process inputs in orders. And in order to prove that, we'll generate a random list. It doesn't matter the type, it can be string, ints. Because we know that fold left is fully parametric, we know that it doesn't matter. So let's say a list of int. And then what we want to do is to call fold left on this input list. And at the end, return the same input list. So it means if we need to return a list of int as a result, it means the default value needs to be a list, and it needs to be the result that will return in case the list is empty. So it means that it's an empty list. So it's a list empty of int, right? Because this is a default value. The default value is called when the list is empty. When the list is empty, we want to return the list empty. Then in the combine function, the first parameter is, if you want, the prefix of the list. It's a state, but it's the list we have processed so far. We assume that so far we have managed to take the first couple of values of the list and keep them in the right order. So this is kind of a prefix, and this will be the current number that we are processing. So what do we want to do with this prefix and this number? Well, we want to add the number at the end of the list, right? Such as, the order stays correct. So how do you append an element to a list or to any sequence for that regard? You use the operator columns plus number. So it took me like probably 8 or 9 years in Scala to finally remember when should you use column plus or plus column, because plus column is an operator you use to prepend to the list, and columns plus to append to the list. They are really difficult to remember. But it turned out that someone gave me a way to remember this. I forgot who it was, but it's a very good technique. Is that it turns out that the column operator is always on the size of the list. So if you want here, we have when we want to prepend, we do plus column because the list is after. While we want to append, we do column plus because the list is before, right? It's quite convenient. Okay, so this will be the result list, and this result list should be the same as the input list if we haven't screwed up. Yep, let's run the test. It fails. It says that the list -1, 0 didn't equal 0, -1. The input is reverse, and it makes sense because I haven't changed the fold left. Fold left normally should be like this. So if we fix fold left, now all the tests are passing. Cool, nice, isn't it? Okay, so if you have extra motivation, I've added a few bonus exercises at the end for you to practice using fold left to implement other functions. I won't go through the answers of these exercises in the video, but as usual, you can find them in the answers folder. So in summary, today we have a good look at the for loop syntax. We didn't cover everything, but we'll come back to this topic in later chapters anyway. We also saw how to iterate over a list or any other data structure and update a variable along the way. Then we discovered that this pattern is extremely generic and that we can capture it using a single higher order function called fold left. And finally, we learned that fold left could be used to implement most of the list API, or at least most of the data processing functions that we are interested in. This means if we find a way to parallelize fold left, then we'll get a parallel implementation for all these methods for free, which is super exciting. So that's all for today, and I hope to see you soon for the next video. Bye.